Hi, so my name is Joseph Tooby-Smith. I am a maintainer of the project Thisline, which is a project to digitalize physics into the interactive theorem prover Lean 4. In this talk, I'm going to talk about interactive theorem provers and their role more generally in mathematics. It's a talk that I gave to the maths department at the University of Iceland as a colloquium. So it's going to be very general, not really going to be focusing on my work. If you're interested in Thisline and the role of interactive theorem provers in physics, take a look at some of the other videos that I've got online. This is a recording of the video. I'm currently in my apartment, so there's no audience here. It's kind of just to keep this video, make it available for people to see so that people can watch it. So feel free to comment. Let me know what you think if you have any questions. So yeah, in this talk, I'm going to look at the role of interactive theorem provers or the role of interactive theorem provers in mathematics. The talk is going to be split into three parts. So first of all, I'm going to tell you what is an interactive theorem prover. It's probably a good place to start with a talk on interactive theorem provers. The second part, I'm going to talk about the past, the history of interactive theorem provers, how they've been used in the past, and what they're currently being used to do right now. Kind of like the current state of things, or things up to the present day. And in the third part, I'm going to look ahead into the future. And really, this third part is going to be focused on the role that artificial intelligence can play in interactive theorem provers and their use in mathematics. So let me start with what on earth is an interactive theorem prover. And to start this, I want to tell you two stories which will first appear unconnected, but then I want to connect them and show you how they're related to interactive theorem provers. The first story is about the Knight Capital Group. So the Knight Capital Group was a financial firm in New York City. It existed till 2012 when it closed down. And it closed down because of an incident that happened on the 1st of August 2012. So the day before, the 31st of July 2012, the Knight Capital Group was putting some new code onto their servers. They had 8 servers which was running this code, and what the code did is it bought and sold stocks. It was basically their server, their code and their service that was doing their financial operations. A technician at the Knight Capital Group was in charge of pushing the new code to these 8 servers, but they made a mistake. They forgot to update one of the servers. So they had 7 servers running the new code and 1 server running the old code. Naively, this seems like it may not cause so much problems, right? The problem was that the new code used a flag that was in the old code but meant something different in both these codes. So the next morning, when the service started, when trading opened, the 7 servers running the new code passed this flag to the server running the old code, and the old code interpreted it differently to how it should have. And the consequence was that it started to buy and sell stocks without really considering what was going to happen, really considering, the price of those stocks and the effect that would have on the money that the Knight Capital Group was making. The consequence was that within 45 minutes, the Knight Capital Group had lost 440 million US dollars. Now, this story is really down to an error or a bug in code. And these sorts of bugs in code are very prevalent across, computer science, computer software development, and more generally. And we had the CrowdStrike incident more recently. That shows you that these sorts of bugs can really have dramatic effects on society. So that's story number 1, naively very far apart, very distant from mathematics. Let me tell you another story so this is story number 2, which will first appear unconnected to story number 1, but I'll connect them in a second. So story number 2 is about this archive paper, HEP-PH 05122112. So HEP-PH is the classification of archive, this preprint surface of papers, for high energy phenomenology. Think of this like a maths paper for now. The reason I've chosen is it happens to be the area that I used to work in, and it happens to be a story that I know about. So what is this archive paper? It's called a QCD summary study of light scalar methods. If you don't know what any of those words mean, don't worry, it doesn't matter. What Hee-Jung Lee did in this paper is he calculated some terms, A1, A2, through to AN, and added them together to get this quantity, this physical quantity E, and then drew some conclusions based on the value of that physical quantity. Now, whenever you put a paper like this on the archive, there's one thing you really don't want to happen, and that is another paper to appear, commenting on your paper. And unfortunately for Hee-Jung, that is what happened, because shortly after this paper appeared, another paper appeared, a comment on a QCD summary study of light scalar metals. And what this comment said was that Hee-Jung had made a mistake, that he had missed two terms, B1 and B2, which when added to the quantity E would invalidate Hee-Jung's conclusion. Now, whenever you put a comment on the archive, there's one thing that you should really worry about, and that is a reply to the comment. And unfortunately, for the authors of the comment, that is what happened, because shortly after this paper, this comment appeared, another paper appeared. A reply to the comments on the QCD summary study of light scalar methods by Hee-Jung, the original author of the paper. And that said, no, the comment is incorrect. The original paper was correct, those terms shouldn't be there, and the conclusions stand. At this point, you may guess where this is going, because shortly after this paper appeared, another paper appeared. A reply to the comments on the QCD summary study of light scalar methods saying those terms should be there. The original paper was wrong, the comment is correct. Eventually, the saga ended with the authors of the original comment saying actually they had made a mistake. The original paper was correct and those terms shouldn't be there. This saga really used up the research time and money of 4 different researchers. And it is ultimately down to an error, a mistake that happened in a paper. And these sorts of errors and mistakes are very prevalent in academia, in some areas more than others. And one mechanism we have to prevent these mistakes is the process of peer review. But peer review isn't perfect. Here's one of my papers, and I'm using one of my papers because I can say there's a mistake in it without really insulting anyone. This is one of my papers that got through the peer review process. It got through me and my 2 co-authors reading this paper, checking for typos. It got through being placed on the archive, people looking at it on the archive. It got through the peer review process, somebody reading this paper, looking for mistakes, looking for factual incorrections. It got through the type editor, yet there are still typos in this paper. And I'm aware that some areas have more strict peer review processes than others, but even in those, mistakes still get through. For those of you eagle-eyed, you may see that the typo is in this bit here. There should be a minus sign here. There's no reason you'd put a 3 here next to this function. You'd put it at the front. Really, there should be a minus sign here. And, you know, this sort of mistake got through to the peer, got through into the published journal. And it makes this sort of stuff unreadable. So why have I told you these 2 stories? First of all, the first story really manifests in the fact that you have these bugs that happen in code. And the second story really manifests in the fact that you have these errors in things like LaTeX or things like academic papers. The reason I've told you these 2 stories is that they're intimately connected. They're really different manifestations of the same problem. If you think of LaTeX as something like C++ or Python, you can think of these sorts of typos or these more conceptual mathematical errors that happen in papers. You can think of them in the same way as bugs in code. They are essentially bugs in LaTeX or bugs in Word. So LaTeX, if you don't know what LaTeX is, it's basically a word processor that you use to write papers. And these sorts of mistakes happen in these sorts of programs. So the fact that these bugs in code and these errors in LaTeX are really different manifestations of the same problem. The fact is that these sorts of programs don't complain when you make an error. LaTeX will complain if you've got a typo, but it won't complain if you've made a mathematical error. And I want to show you this in this text box, which you can think of as acting very similar to something like LaTeX. So I can say that f be a function from the natural numbers, let me call that nat, to the natural numbers, and let a be an integer. Then f is equal to a. So if you were to write this in LaTeX or something like Word, it would not complain. But those of you that are mathematically minded will realize that this sentence makes absolutely no mathematical sense. There's no way for you to set a function f from the natural numbers to the natural numbers equal to an integer a. It just doesn't work. It's mathematically incorrect, but you could write that in a paper, and it would take a human to look at that and see that there's a mistake. Same sort of thing happens in bugs in code. There are certain bugs in code, for example, if you miss a minus sign, that you would only ever spot if you really carefully looked through the program, or you find an edge case that happened to cause the error. So what's the solution? Well, the solution is to use a concept, or a solution rather. It's not a perfect solution, it's part of a solution. It's the concept of correct by construction. That is to use, for example, a language, a word processor like LaTeX, or a programming language like C++ or Python that doesn't let you make these sorts of mistakes. It just won't compile, it won't give you the output if these sorts of mistakes happen. And these programs exist, and they are called proof assistants, or as you can probably guess by the title of my talk, interactive theorem proofers. And they are programming languages that don't let you make these sorts of mistakes. They give you an error. And they can be used both in mathematics and in computer science, programming languages and software development. And this is kind of how those two stories, naively disconnected, that I told you at the beginning of this talk, how they are connected. So let me give you some popular proof assistants. So there's Rock, or which was previously called Coq, they recently changed the name. There's Isabel, there's Lean, and there's Agda. Let me move myself down a bit. And all of these programming languages, all of these proof assistants, have very different features about them and are used by slightly different communities. So Rock is particularly of use in the homotopy type theory community. Lean is used a lot by classical mathematicians, people working on things like number theory, differential geometry, topology, things like that. Agda is mainly used by computer scientists, basically because in Agda everything is computable, and Isabel is used more generally by a broad range of people from different communities. So my background, basically because I'm building Physcene, which is a project to digitalize physics into Lean, my background happens to be in Lean. You can probably guess that from the name of the project. So a lot of what I'm going to talk to you about in the rest of this talk is going to be focused on Lean. But what I'm going to say holds more generally to some of these other theorem proofers. So the first thing I want to do is give you an example of Lean. And if you want to interact directly with this example, you can go to my website down here, where there are slides. So you go to my website /slides/Iceland2025.html, and you'll see these slides and you'll get this little code snippet. So I'm going to come out of this because there is something weird with the software that I'm using. I have to refresh my page to get things to appear. And so this is what Lean looks like. So the first thing that I wanted to do in Lean, which you can think of it as something like LaTeX, or you can think of it as something like a computer programming language. The first thing I wanted to do was to show you that it will complain if you make a statement which is mathematically incorrect. So I'm going to use the statement that we had before. I'm going to say example, and this is just some Lean syntax to get things to work. I'm going to say let f be a function from the natural numbers to the natural numbers. And I'm going to say let a be an integer. Then I'm going to say, well, let's try and state that f is equal to a. And then I'm going to put some more Lean syntactical sugar, basically to close the line. And we'll see let me put a space here, we'll see that Lean has complained. It's put a line under A, the same sort of line that you'd get if you made a spelling mistake in something like LaTeX. It's got a line under this, and if we hover, it says there's a type mismatch. A has type sed, so that is the integers, but it's expected to have type nat to nat, or it's using this boldface blackboard bold notation for the natural numbers. So it's expected to have type a function from the natural numbers, but it is a type integer, and you can't set those two things together. So what is a type? Well, a type is very similar to a set, and it has elements. Typically, the elements of a type are called terms. And Lean and a lot of these other theorem proofers, their mathematical foundation is this thing called type theory. So that is the thing that they are all built upon. And to give you an idea of how they work explicitly, I thought we'd do an example starting basically from nothing to define the natural numbers. And this is kind of like the first example that you would see in a lot of these theorem proofers. So what is a type? A type is, like I said, as I've said, and it has elements. And to define a type in something like Lean, so let me move all of this up. So to define a type in something like Lean, you need to specify the elements. So what are the elements of the natural numbers? Well, we have 0, we have 1, 2, 3, etc. Okay, so let's start with 0. So we're going to define this thing called my type, my nat, basically not to interfere with this nat, which comes from this library mathlib, which I talk about a lot in what follows. So we're just calling it my nat to stop there being a name error. And we're going to define this type inductively. And this is basically the fundamental way that you define types in Lean. So how do we define this? Well, it's got the element 0. So we write this bar, and then we say that we want 0 to be a type of mynat. And I will accept it. So now, actually, mynat contains one element, and that element is 0. And what are the other elements? Well, it's got 1. So we can put 1. So now my nat has two elements called 0 and 1. We'll give it a second before for this error to disappear. There we go. We've got 2. So let's put 2 there. Okay. Right. And we've got 3, so we could put 3. But you can probably see that this is probably not the way to go, because we could be here quite a long time if we were to give every single element. So what you can do in Lean is define things inductively. So you can say, well, actually, so I've got the type for the natural numbers. I'm going to say the natural numbers instead of my nat. For nat, you have to type the element 0, and then for every other natural number n, you've got another natural number n plus 1, called the successor. So if you've got 0, then you've got 1, because 1 is the successor of 0. If you've got 1, you've got a successor of 1, and that's 2. So we can actually define things inductively. So we can say that the natural numbers have this element 0, and then for every natural number n, we have another natural number called the successor. And this is saying that, so this definition of this type is saying that you've got an element 0, and then for every natural number, you've got the successor of that natural number, which is also a natural number. And this is how you define the natural numbers in one of these proof systems. And this is how you define the basic fundamental types. And when you've got the fundamental types, I'm just going to take a drink of water, you can start to construct other types using some sort of constructors. And one of those constructors is the function type. So given a type, you can define a function type. So, for example, addition is actually a function type from the natural numbers, two functions from the natural numbers to the natural numbers. In other words, it takes two natural numbers and it gives you a natural number out. So how would we define this in Lean? And you can define functions in these programs in the same way that you can define functions in, for example, C++ or Python. So to define addition, we need to tell it where it sends the natural numbers. So we can say that it sends 0 the addition of 0 and any natural number n. We send that to the natural number n. And we can say, send the successor of m and the natural number n to the successor of the addition of m and n. I will notice something here, that this definition is recursive. So I defined addition using addition. But Lean is smart enough to know that this addition takes the successor of m, whilst this addition takes just m. So this is saying you've kind of gone one down the inductive step, and Lean is clever enough to work out that that terminates. So this all looks like mathematics. It kind of may look a bit like programming, but really this is kind of can be thought of as both programming and mathematics. And we'll see in a second that you can prove theorems using these results, but they're also executable functions. So we can execute this addition. So we can say if add, and we can say, let's add the successor of the successor of 0 to itself. So what is the successor of the successor of 0? Well, the successor of 0 is 1. The successor of 1 is 2. So this is 2. And this is again 2. So 2 add 2 is 4. And we'll see up here that this thing here, we have 0, the successor, that's 1. 2 successor, that's 2. 3 successor, that's 3. 4 successor, good. So 2 plus 2 is 4, which we would expect. So you can execute functions, and this is one way that this can be used to interface between programming, can be used to do programming as well as to do mathematics. So let's give another function called multiplication. Okay, so let's define this in a similar fashion. So the multiplication of 0 and a natural number n is going to be 0. And the multiplication of a natural number m, or the successor of the natural number n, and n is equal to what? Well, so this is m plus 1 times by n. So we can write this as the addition of n times by the multiplication of m and n. So I want you to notice two things about this. First of all, again, this is a recursive definition, which is fine. Lean can work out that this terminates. If I put the successor of m here, for example, it will give me an error that it can't work out that this terminates. But given we have just m here rather than the successor of m, it's perfectly happy with that. And notice that I've also used addition. So I can use functions to define other functions. And in a similar fashion, you'll kind of see this a bit in a second, you can use lemmas and you can use theorems to help prove other lemmas and theorems. So let's talk about lemmas. To kind of bring this to the more, mathsy side of stuff, how can you use these theorem provers to do mathematics? You can use them to do mathematics because you can use them to prove stuff. So in Lean, we can write things like this. So this is the saying that A, B, and C are natural numbers, and this thing here is true. So equality here is something called propositional equality. You can just think of it as equality. And we want to prove that the addition of A plus B add C is equal to A add the addition of B and C. In other words, addition is associative. And we can try and prove this. So the way that this really works in Lean is that this thing here is just it's another type. It's something called a proposition, but you can think of it as a type. And a proof of this type, or a proof of this proposition, is given a term or an element of that type. So, but Lean has a bunch of tactics that we can use that will help us give an element of that type without necessarily having to do things very explicitly. So let's have a go at this. We want to prove this lemma here. So how should we do this? And let me start by saying Lean is really helpful because if we look over here, it tells us what we need to prove and it tells us what we have at our disposal. And as we go through the proof, this tactic state here is going to change based on the tactics that we use and the sorts of things that we imply. And really the goal is to try and manipulate this thing here into true, into something that proves the relation. So what can we do? Well, we have A, B, and C, which are natural numbers. And the only thing we really can do, we don't really have any theorems yet. So the only thing we can really do is look at the cases. So we can say, let's try and take A to be 0 and then the successor of n. So basically we want to do induction on A. So we can type induction A with, and we look at the 0 case. I'm going to write sorry, and I'm going to look at the inductive case like this, and I'll explain all of this notation in a second. But first, let me explain this tricky thing called sorry. So what sorry is basically a way of proving a theorem with an axiom. So in Lean, there are some built-in axioms that basically help you prove stuff. And the sorry axiom is basically the axiom that anything is true. So you basically put sorry there when you don't want Lean to give you an error. So if I remove it here, it will give me an error. But you also don't want to give it a proof. And you can track the fact that theorems depend on sorry, so you can't really, you've used this in the future. But it's kind of like a placeholder when you don't have a proof yet, just to stop Lean giving you an error. And that's what sorry is. And it's based on a built-in axiom within Lean. So you notice that in this inductive case, so this first thing here, this is the 0 case, and you'll notice that Lean has replaced what we had. Let me put my cursor here. Here we had A, and if I put my cursor here, this A has been replaced with 0. So we now want to prove this thing here. But if we think about this, 0 plus B is equal to B. And B at so this thing here is just definitionally equal to B at C. 0 add anything is just anything. So this here is also definitionally equal to B times by C. So actually, this is definitionally true. And Lean can work that out. And what we type when something is definitionally true is REFL. And that's basically saying, you know that this is true, work it out that it's true, and Lean will do that. And notice my tactic state has been reduced to no goals. So now let's look at the successor case. In the successor case, you will now notice that I've got this IH, which is my thing I put here, and I can hover over that, and it will tell me what it is. So IH is this statement here. And you'll notice that in my tactic state, I now have that at my disposal. And this is basically the inductive hypothesis. So my goal is based on the successor of M, but this inductive hypothesis is a statement that is true just for M. So how do we prove this? Well, there's a lot of hammers in Lean, basically tactics that do a lot of the work for you. And one of the main tactics that does a lot of work is the tactic simp, basically meaning simplify. So we can just try and simplify this expression. And we can add to simp the definition of addition like this. So simp uses a database of results, and you can add results to the simp database, but you can also add results explicitly like this. And we can see that this is the state before simp, and after simp, it reduces down to this thing here. So simp basically reduces our hypothesis, and it removes the successors. And we can put a question mark after simp, and it will tell us what it's used. So it's used addition and the fact that the successor is injective, and it works that out for us. So this is a lemma that we get for free from Lean, and it's reduced our hypothesis, our goal, to this thing here. But this is exactly the same as our inductive hypothesis. So we can actually, here, just do exact IH. That's basically saying what you've given, the goal is exactly the same as one of my hypotheses, IH, and therefore this is true. And if I remove the sorry, I get no errors in this thing, and that tells me that this is true. I have given a proof of this statement. Lean doesn't actually care about the proof. It can track what that term is. So we could write show term here, and it will show us the explicit term of this type, which we've constructed, but it doesn't keep track of those for lemmas because they're not so important. So this is how you prove stuff. And if you wanted, you could use this lemma, kind of as this lemma has been used, you could use this lemma to prove things in the future. To give you an idea of how things work more, or to give you really show you how powerful some of these tactics are, I want to try and prove this theorem here. So this is a statement that if I have A, B, C, and D are integers, that this expression here is true. That A plus B times by C plus D times by C minus A is equal to A plus B times by D plus C. Sorry, A plus D times by C. So if you were to prove this explicitly, you use the fact that this A here cancels with this A, then you use the fact that multiplication is distributed over addition from the right, and that you could use like, rewrite rules to go rearrange things explicitly, or you could use a hammer in Lean called ring, which proves this for you. And I'm showing you this because I think a lot of people, when they think about interactive theorem provers, think about or already think about worry about the fact that you have to do a lot of these small things by hand, but actually for a lot of these theorem provers this isn't the case. There's a lot of hammers that really do a lot of really built-in tactics that do a lot of the trivial stuff for you. So hopefully that has given you a little bit of the flavor of what these theorem provers can do and how they are used, and the fact that they give you computable, executable functions, but allow you to write proof theorems in mathematics, reuse stuff. So to summarize basically how Lean works, it's based on this thing called type theory. It allows you to define, so you have types are defined basically inductively on their terms of types, based on their terms, sorry. And given types, you can construct new types. So for example, you can take this function type that we saw, you can take the product types, you can take sigma types, you can take pi types, different types of types built upon other types. Propositions can be thought of as a similar to types, and really a proof is basically providing a term for a type. And remember, you can think of a type very similar to a set. And there are some built-in axioms, and some of these axioms differ between some of the interactive theorem provers that you're using. So, for example, Lean has the axiom of function extensionality, which says that two functions are equal if and only if they're equal on all inputs and outputs, but Anchor doesn't have function extensionality. So you can't use that. So some of these systems have more liberal axioms than others, but they all have some foundational axioms. So there are a number of advantages to using proof systems, which I've written here. So the main one is correctness. You can be sure that the theorem that we proved, that addition of associative, is true, based on the foundations of Lean, which is type theory. So assuming that Lean, the core of Lean is sound, that theorem is true, and one can be pretty sure that the core is sound. Tactics. So another advantage is that you have these powerful tactics that allow you to prove stuff very easily, and these tactics are only getting more powerful. They are basically the hammers that you can apply to simplify your proof down, to make it easier to solve. And really, a lot of these tactics and working out which is the best tactic to apply is a lot of what's involved in the game of theorem proving in one of these interactive theorem provers, and you can really think about these things as a game. Lean and these interactive theorem provers know what the things are that are present in the system. So remember when I did that example with this function and this integer a, Lean knows that that thing is a function, and it knows that a was an integer. It knows that f was a function, and it knew that a was an integer, and it knew that you couldn't equate them. But that also means that Lean, if you use that, you can search Lean and the sorts of theorems and the sorts of definitions in Lean much more easily, because Lean knows what these things are. So you can ask it for something like, imagine you have an integer equal to another integer. What sort of theorems do you have there? It doesn't depend on, the specific syntax that you have. And this makes it easy to search for mathematical theorems and results in these systems. Results are reusable. The thing that I like to say is in these systems, you only ever have to prove things once. When something's been proved into Lean, anyone can reuse it. You don't have to prove it again. So this kind of brings things more into the like collaborative effort of stuff, things only have to be done once. You can improve the proofs, but you don't never have to really prove things again. And things are executable. So functions and definitions are executable. This is not always the case. In fact, so something like Lean has classical choice, which means that some things aren't actually executable. But in interactive theorem proofs like Agda, everything is executable. You can execute all of the functions. And this allows you to, build this bridge between mathematics and computer programming as well. So this concludes the first part of this talk. In the second part, I really want to talk about the history and the current state of these theorem proofs. And really, this is really the history according to me, my perception of the history. I'm aware that I may not be given the most accurate description, so feel free to, disagree with what I'm going to say. But the way that I like to think about things is that there are two eras to formalization. There's the pre-2017 era and there's the post-2017 era. And the pre-2017 era was really characterized by one-off projects. So here are a number of ones. In 2024, we had the prime number theorem was proved into Isabelle. Again, in 2004, we had the four colors theorem proved into Rock, previously and back then called Cog. In 2005, we had the Jordan-Kerr theorem in Isabelle. In 2013, we had the odd order theorem proved in Rock. And between 1998 and 2015, we had the Kepler conjecture, which is related to sphere packing, proved in Isabelle. And this is a fun story about this, is that Hales produced a proof, a handwritten proof of, or a typewritten proof, let's say, of the Kepler conjecture. And this proof was like 250 pages long. And he sent this to a journal, and the journal was like, okay, we're going to get a team of reviewers to try it and see if your proof is correct. And so they got a team of 12 reviewers. And after a couple of years, they came back and said, we can be 99% sure that this proof is correct, but we can't be 100% sure. So they didn't accept the paper. And what Hales did is he split his proof into a part which they were absolutely sure about. And then for the other part, they spent 17 years formalizing it, writing it into one of these interactive theorem provers to show that undisputably it is correct. And this was kind of like the first big long running project. That's probably a statement I can't justify, but this is a big long running project that had been going on for years, and they finished it in 2014, 2015, proving the Kepler conjecture in one of these theorem provers. And to kind of give you an idea of the current opinion or a sense of what was going on, the thoughts and feelings of mathematicians about interactive theorem provers in the pre-2017 era, I'm going to take the story from Michael Harris's blog, which is about the November 2014 Breakthrough Prize ceremony, in which Rory Milner asked the question, is anyone willing to bet that computer verified proofs will not be widespread in mathematics in 25 years? And on this panel was Jacob Leary, Richard Taylor, and Terence Tao. And I apologize if I pronounced any of their names wrong. So Jacob Leary responded, I'll take that. So basically, Jacob Leary did not think that computer verified proofs will be widespread in mathematics in 25 years. Richard Taylor said, yes, me too. And Terence Tao, slightly more optimistic, said some people will be working on computer verified proofs in 25 years. And I'm not gonna, state that this was the actual hard belief of these people. This is a story taken from a blog, and there are some comments on that blog post. But this kind of gives you a feeling of, what these people, or what the current feeling about proof systems and interactive theorem proofers was back in 2014 on the pre-2017 era. And in my opinion, times have changed. We're not 25 years after that point. We're about 10, 12 years after that point. But I think there is a community where this is now starting, interactive theorem proof is now becoming more widespread, and this is a growing field. So, The post-2017 era, so that was really all about the pre-2017 era. The post-2017 era is the era where open source met mathematics. So open source projects have been, used heavily in computer programs. There's this whole thing about the Apache way, creating projects which are based on voluntary work, based on, doing stuff for the better good, making things usable and collaborative and all working towards a common goal. And I would say that the post-2017 era of formalization in mathematics is really characterized by big open source projects, in particular, the project MathLib. So MathLib is, we kind of came across this earlier. MathLib is a monolithic library of mathematics formalized into Lean. So it's a library containing a bunch of results from mathematics from different areas, formalized, written into Lean that anyone can contribute to, and anyone can use the theorems and results in their own proofs. It was started in 2017, and it currently has over 400 contributors. And these numbers are slightly out of date because it currently has over 100,000 definitions and over 200,000 theorems from mathematics written into Lean, which you can contribute to and you can use in your own proofs, as I said. And it was heavily promoted initially by Kevin Bussard. And it contains a bunch of different areas of mathematics, and I listed through down here. It contains algebra, algebraic topology, category theory, condensed mathematics, geometry, group theory, measure theory, number theory. So basically a range of different areas from mathematics, and some areas are slightly more formalized than others. People say formalized means that things have been written from pen and paper into Lean. So topology is quite heavily formalized, number theory is quite heavily formalized. Things like differential geometry, unfortunately, aren't that so well formalized. But these areas are growing and people and more people are contributing to it. So let's take a look into MathLib. And one of the ways that you can explore MathLib, if you even don't know anything about Lean, is to use some of their search engines. So one of those search engines is called Lugo, and there are more sophisticated, more AI-based search engines out there that also allow you to search MathLib. I'm going to use Google for this. I'm not saying it's the best. I'm just saying it's one of them. So one of the ways you can explore these repositories is to use these search engines. So let's say that we are a category theorist and we wanted to learn something about, and we knew there was something related to epimorphisms and the composition. So we could say epi, okay, and let's try comp and let's say category. So we can search for those things. There's some syntax you have to get used to with these search engines. But if we type find, we get a list of results related to these concepts. And let's take a look at this first one and let's see what it says. So this is a result that's in MathLib, and it's something that if we were trying to formalize our own results into Lean, we could use. So what does it say? It says that C is a type. This U is a universe level. Let's not talk about or worry about that. This says that C is a category. The X, Y, and Z are objects of C. The F is a morphism in the category from X to Y. This arrow here is a slightly different arrow to the one we saw before for functions. The F is an epimorphism. The G is a morphism from Y to Z, and that G is an epimorphism. Then, so this really means then, the composition of F and G, which is this thing here, is also an epimorphism. So this is saying that the composition of two epimorphisms in a category is also an epimorphism. And if we wanted, we could click on this, and that would take us to the documentation. Scroll up a bit. It says the composition of epimorphisms is again an epimorphism, and there's some implementation note. And if we wanted to, we could click, we could explore the source code. And you can see that this is the proof of this statement. And one of the things about MathLib is that the proofs are often very short. And the reason for this is that in MathLib, they tend to build what's called an API. And that is basically they take an area, like category theory, and they break it down into really small lemmas and really small results that can be used by other people and that make proofs in the future smaller. or easier to do rather. So instead of having big long proofs of things, they break their proofs down into smaller things, into usable, reusable lemmas that are more generally useful. And this is kind of why a bunch of the proofs end up really small. So let me go back to my slides. So despite this era being characterized by, big open source projects, that doesn't mean to say that these big target projects don't exist. So, for example, like the Kepler conjecture. And there are a number of ongoing projects to formalize big areas within Lean. And I've written a few here. So Kevin Buzzard and Rich Taylor are working on this project to formalize Fermat/theorem into Lean. Emily is doing something related to infinity cosmos theory. So that's infinity category theory, infinity topos theory. Um, that sort of area. And Terence Tao is looking at this theory of equational theories. So one thing you'll notice about all of these projects is that after the names, I put et al. And this is because all of these projects are big open source projects. These people that I've written down are really the heads or the people that are organizing the project, but they are big projects. So if you wanted to go and contribute to these projects, you could. You could go learn Lean, and they're open source projects that anyone can contribute to. And this is kind of why these is now, still part of this open source type community. So how do these projects work? Let me look at the Fermat/theorem project. The way that this project works is that there is this thing called a blueprint. And what the blueprint is, it is It is a list of results or theorems written in English. So we have these theorems here, and this is connected to Lean. And there are graphs. Let me take this one. There are graphs like this, where each node contains a theorem or a lemma, and depending on the color, it tells you if that theorem has been proved or not, or formalized into Lean. And the idea is that people write these blueprints, and then it becomes an open source collaboration, an open source community to try and formalize all of these nodes. And the results of these projects usually end up getting put into MATLAB eventually, or upstreamed to MATLAB, so that they're part of this bigger library, so that they're all maintained together and they can all be used, um, as part of one big library. So this kind of really is what is happening at the moment in this area. It's really characterized by these big open source projects. And this is kind of, you get a lot of benefits from doing this. Basically, everything becomes collaborative. People don't waste time working on the same thing. Things get maintained a lot better. Everything is kept with the same version of Lean. Things interact a lot better with one another. So what's my part in this whole story? As I've said at the beginning, my background is in physics, and I kind of created and maintain this project called PhysLean, which is a project to digitalize physics into Lean 4. So it's basically like MATLAB, but for physics, focusing on results from a broad area of physics so that people can use those results and we can build the akin of MATLAB for physics. So if I take a look at the documentation, we go down here to PhysLean. You can see that it contains things from like classical mechanics, condensed matter theory, quantum mechanics, quantum field theory, relativity, etc. Some of these areas have more stuff in than others. And again, this is an open source collaborative community, so that if you want to come and join, please do. Please contribute in any way that you can. So for the rest of the talk, I want to go in and discuss the future and really what the future might look like. And because, when I give these types of talks, the biggest question I get is about artificial intelligence. Let me talk. I am, for this part of the talk, going to focus on the role that artificial intelligence can play in interactive theorem proofs. So the reason that interactive theorem proofs and artificial intelligence are even, talked about in the same breath is that theorem provers can provide automatic feedback on proof correctness to AI models. In other words, a theorem prover can tell the computer without a human coming in whether a proof is correct or not. So the AI could, for example, write the proof, Lean could give it feedback on whether that proof is correct or not without a human coming in to check whether things are correct. So this gives a way that, it can remove computers from the loop about proving stuff and really makes this a game for the computer as it is for humans to try and prove these results. So to give you a story, in July 2024, a team from Google DeepMind, on the day of the International Math Olympiad, were locked into a room. And they were given the problems that the students in the Math Olympiad were trying to complete. So a human manually took those problems and wrote them into Lean, and then they set their computer running to see if they could solve them. So in the International Math Olympiad, there are 6 problems, and their computer managed to solve 4 of them. So it managed to solve 2 algebra problems, 1 number theory problem, and 1 geometry problem. It didn't manage to solve the 2 combinatorics problems. So these prove that these AIs can do quite a lot when it comes to these like mathematical type problems. The catch is that it took the Google DeepMind computer 3.5 days to solve these problems, whereas it takes a student, or a student only gets 4 hours. If you were to rank their computer, how it did compare to students in the International Math Olympiad, it would have got a gold medal. But one of the conclusions that one can draw from this story is that there's currently a lot of focus on solving these competition type problems. So there's a lot of companies, a lot of AI teams trying to work on, coming up with AIs that are good at solving these competition type problems. And these lead to these leaderboard type things. So here's an example of this Putnam leaderboard. I'm very probably pronouncing that incorrectly, so I apologize. So this Putnam is a mathematical competition in Northern America, and they have formalized 650. So they formalized the problem of 657 problems from this competition, and different AI models are used to try and solve these. And there is a leaderboard on how many they try to solve, and there's some for different proof assistants. But you can see that the top one out of 657 problems managed to solve 10 of them, which to me isn't so impressive. But it's still, it does manage to solve some. And these things are getting better. There's DeepSeek Prover version 2, which did better than this, but isn't on this leaderboard yet because I don't think they've checked all of the results. So instead of, taking these leaderboards at face value, I thought I would show you an explicit example of these AIs in action. So I'm gonna give this Kim in that. I'm really bad at pronouncing names. So I'm gonna take this first model here, and we are gonna give it a problem from Lean, and we'll see if it can solve it. So I'm gonna give it this problem here, which and we're gonna ask it to solve this lemma. And you notice that this is the lemma that we solved at the very start of this talk, that addition for this type is associative. And we'll see how well this AI does. So luckily, the team behind this model have provided us with a nice interface that allows us to use it to test our problems on it. And you can enter the problem in natural language, and it will try and convert that into Lean. So that's called formalization, like auto-formalization of the problem. But I'm going to give it the problem, and we're going to try and see if it can generate a solution to it. And I'm going to give it 16 passes, so that means it's going to have 16 attempts at this, and we'll see what happens. So you will see, so the thing that I expect to see here, each of these 16 numbers here are the passes. They will either go red if it failed, or it will go green if it managed to solve it. The thing that I would expect for this problem is that it should be able to solve it in a lot of the cases. And the reason for that is that this problem is fairly standard. It's probably on GitHub a lot. It's kind of like one of the first examples you would see if you were to try and prove something in Lean. So there's probably a lot of data behind these things that it can copy and try and solve this problem. And you can see that in some of the cases it has solved it, in some of the cases it hasn't. So let's look at the solution of this case where it solved it. And let's see what it did. So it matched A with 0 and then the successor of A, and then you simplify. It didn't need to simplify there. It could have used REPL, which would have been a shorter tactic. And then for the successor case, it used the inductive call of addition and omega. And omega is just like a powerful tactic to solve this thing. So it managed to solve it. It basically did it in the same way that we did it. Use some slightly different tactics, but the ultimate idea is the same. You do induction on A, and you use the recursive call in the successive case. So good. Let's see how many cases it did. So it's done like maybe just under half of the cases it managed to solve it. Let's take a look at a case where it didn't solve it. Let's see what it did. So here it tries to do induction on C, which probably wouldn't work because our definition of A was really defined through induction on the first argument, whilst it's trying to do induction on the last argument here. So that wouldn't have helped. So that didn't provide a valid solution. Good. So I want to now, so this is kind of like the sort of stuff that I would expect these AIs to be able to do. I kind of now want to show you a more tricky example. And this theorem is a theorem that I personally came across when I was trying to formulate some results from physics. It's related to a tight binding chain in condensed matter physics. And it is basically the statement that if I have a natural number n, I have a real number a, and I have a number n which is between 0 and n minus 1, then this number, this minus pi over a, is less than or equal to this number here. And you can prove this. This is for sure true because I proved it in Lean. So this double arrows is basically saying treat this thing as a real number, and this n over 2 is saying divide the integer n by 2, take the floor of that, and then convert that thing into a real number. And so this is true. One can prove it's true, and it's the sort of stuff that would be helpful to me when I'm trying to prove things in Lean if these systems could do, because it would save me a lot of time. So we're going to give this to the same AI, and we're going to see how it does. So again, we're not going to worry about it trying to formalize the natural language problem. We want to give it the problem as a Lean statement, and we want to get it to generate the proof. And we're going to give it 16 attempts here, and we'll see how well it does. And I can tell you how well I think it's going to do. I think it's not going to be able to prove this in any of the cases. And the reason for that is that this proof requires you to pull basically a rabbit out of the hat, to come up with some thought process that allows you to prove it in a clever way. And typically, in my personal opinion, again, I'm not claiming I'm an expert on AI or anything like that. These sorts of things don't tend to be that good at this. On a personal, like, I've tried to use these to prove things, and we'll try and see that with these proofs. I should say that also I know that this proof it hasn't appeared like in the training data of this model. It's a new proof. It is on GitHub, so if they updated it very recently, they may have been able to put it part of the training data, but I think it's unlikely that it was ever, or a proof like this was ever in the training data of this model. So we can see in the case of 14, it failed. And we see what other cases. So 10, 13, and 15 has failed. 8 has failed. 7 has failed. Free sales. Whilst we wait, I should say it's really nice that the team behind this model has made this program that allows you to mess around with these things. I think if all of these AI companies made something like this, where we could, test their models with and use their models with things that are problems that we actually come across, they would get a lot more usage by the community. But again, I'm not an expert on AI. Definitely not claiming that the quality of any of these sorts of things. I'm just showing you from experience what type of things they can solve and whatnot. Okay, so we can see most of the cases has failed. I suspect it's going to fail in all of the cases. Still doing a couple. Let's take a look at some of the proofs. Let's see what it does. So it tries to give an explanation of its proof. So it tries to justify the proof, which is what all of this text is. Okay, so it's trying to give a proof here, and it's basically trying to do things using Linafa, which is, I'm probably pronouncing that wrong as well, which is like a tactic that allows you to solve linear equations. So yeah, I'm not quite sure what's wrong with this. Basically, it tried to apply Linafa when it didn't work. So let's take a look at another case. Here it tried to prove that n is equal to 0, which it's definitely not equal to, because you can take n to be any natural number. There's nothing in the hypotheses that say n should be 0. So, yep, that proof would not work. Let's take a look at this one. Again, it's trying to use Linafa. And again, it failed. So it's trying to use these like hammer tactics that can be used to try and solve things. Yeah, sometimes it like just tries and applies the same tactic over and over again. There's not an example of this now, but this is something that some of these models tend to do. So let's see if we wait for the final two, just in case they happen to solve it, and then I'm be pleasantly surprised. Okay, I am gonna go forward because they are taking their time, and I'm not sure if that's their server error or something, or just things have been slow. But I'm going to go forward, and we'll just maybe live in curiosity whether those last two cases were solved or not. So the takeaway message that really I have is that we're quite far away from this being useful. They are useful in some proofs. They are useful to do more of the basic stuff, but I don't think we're at a stage where any of these AIs are proving, really useful, novel stuff that are the things that are really the difficult things when it comes to interactive proofing lemmas and proofing results in interactive theorem provers. Things like GitHub Copilot, and some of these and these models are good at, like repetitive stuff that they've seen all like a lot. But when it comes to try and prove stuff, the difficult things, the things that you actually have to think about, why is this true? They're not so good at. And because people like predictions, this is a random prediction. Maybe we're 10 years away from this. Maybe we're closer. Maybe we're further away. We're always 10 years away from something. So maybe this is something we are 10 years away from. So with that, I'm going to conclude. So thank you for watching. Yeah, if you have any questions, feel free to put them in the comments. Feel free to contact me either by email or on LinkedIn. But yeah, thank you for watching. Hopefully you've taken something from this talk. And yeah, if you're interested in physics and lean, come to the Lean community. Come to the Lean Tulip, discuss on there. Let me go back just to see if it solved any. If this finished, it did not. So I'm going to finish this video there. Thanks for watching.